Okay, time to get started. So last time we finished section 1.6. Recall I do 1.6 first because it's a bunch of linear algebra review, and I like to get the review out of the way as soon as possible. So back now to 1.1, about which I'm going to say very little. Because I believe y'all know all of what's in 1.1. It's all a really basic linear algebra if you get right down to it. So, couple of comments. I noticed the book likes to use bold to indicate a vector. I feel like they're showing off because by handwriting, it's so much easier to write a little vector hat than to sit there and bold. You know, we have to go over it several times. It's silly. So I have a significant preference for this vector hat. Y'all can do whatever you want. If you want to sit there and bold, that's okay, right? But I don't think it's a good investment of time. The other thing I want to comment on is it kind of bugs me that the book likes to represent vectors sometimes like this. I think that's weird. I mean, I get it. It as written, it says the arrow from P1 to P2, right? So in some sense, it's very natural. But once you learn a thing or two about vectors, right, and the algebra of vectors, which again, I know y'all know, not hard to persuade yourself that this is also P2 minus P1. Keep in mind, P2 being a point is also a vector, right? And P1 being a point is also a vector, or at least they're naturally associated to vectors. So P2 minus P1 says the same thing. Now, so what's the preference? You know, why is it that I would have a preference for one versus the other of these? And it's because this one shows the algebra. Algebra is a good thing, right? Algebra is our friend. If there's an opportunity to see algebra, possibly use some algebra, wouldn't we want that to be visible in the notation? Now, that's just my take. I suppose you could argue it's one pencil stroke less to write it like this. To me, that's a price I'm willing to pay, right? And anyway, that's just my gripe. But again, doesn't really matter, and you can do whichever you like. But I hope you'll consider this one. Okay, is everybody okay? Right. Okay, so there was 1.1. We just finished this section. Okay, 1.2. Now again, there's a bunch of stuff in 1.2 y'all have seen before. Again, let me remind you, tough choices, right? I can't go walk through every paragraph of the book. We just don't have the contact time to do that. I'm going to spend most of my time in 1.2 talking about parametrizations, which I imagine most of y'all have not seen before, or if you have, maybe not much. And it's going to turn out that parametrizations are really important for stuff we're going to do later in this course, and also some of the stuff soon. So first of all, what is a parametrization? Let me go ahead and zoom all the way out here. A parametrization is a function that gives position as a function of, I'm going to say, time. You don't have to be time, right? It could be position as a function of some other parameter. You could call the parameter Q. It doesn't matter, right? But what's nice about thinking of it as time is if you have position as a function of time, you can think of a parameterization as drawing the curve for you. That it's not just that the curve is drawn, but that the parametrization is the process of drawing. It's like a little movie of the curve being drawn. So let me show you an example of that. And I guess I will zoom back out to give myself a little bit of more space to work. So if we look at this parameterization right here, notice we have position xy as a function of time, which is, again, the only variable that shows up in the formulas for position, right? So position is a function of time. And now we could start plotting points here. And let's plot a few. So here's an xy system. And let's plug in certain values of t. Let's plug in t equals 0. What happens when you plug in t equals 0 into here? Well, you get 1 comma 0. Right? What happens if you plug in t equals a slightly larger number? Well, think about what cosine and sine do. And the next, well, a short time later, you're here, and then a short time later, you're there. And if you just go through and plot points, it'll do like this. So as t increases, you are literally tracing out a curve. So I think it's a nice way to think about a parametrization. How are we doing? Everybody with me? Now it kind of looks like a circle. Right? And in fact, not hard to show, this actually is a circle because, check it out, x being cosine and y being sine, this parameterization gives formulas for x and y, and those formulas for x and y always satisfy that equation, which we know from long ago in high school that is a circle. So this parameterization, every point generated by this parameterization is on the circle. And that means that this thing that looks like it's tracing out a circle is literally tracing out a circle. Is that cool? All right. Okay, here's another parameterization. Right here. There you go. Notice position is a function of time. Now I've written it a little bit differently here, right? But in particular, this is an x and a y. So this formula, where you have a formula involving t, comma, another formula involving t, that expression is position as a function of time in the plane, in the xy plane. Okay, so what is this parameterization? How can I understand what this looks like? There's different ways to do this. I'm going to show you, by the way, very often what I'll be doing in this class is not exactly showing you, how to do it, right? But there may be different ways of doing problems of this kind of sort. And so I like to think of it as I'm going to give you all tools. Right? And my little silly metaphor is that everybody's walking around in their head with a toolbox, and I'm going to give you tools for your toolbox, right? So don't think of this as the way to do it. Think of this as a useful tool for these kinds of problems. So here we go. First tool. Let's see here. Let me get my stylus set up right. Step 1, solve for t in the first equation. That was easy in this case. Right? Next, take this formula for t, plug it into the second equation. Now keep in mind, this second equation here is telling you y as a function of t. So when you plug in this formula for t, namely t equals x plus 1, right? Altogether, notice your y equation becomes y as a function of x, which you can then rewrite, multiplied out to terms. And boom, you've got an equation now. We have successfully now translated a parametrization into an equation, something more familiar. And in particular, this is very familiar. This is the equation of a line, right? That's like middle school, something like that. This is old news, right? The equation of a line. So this purple thing is a line. How are we doing? Everybody see the process there? Okay. Now, bad news. Sometimes this very first step, solving for t, sometimes you can't do it. Right? You can't always solve for everything you want. Sometimes algebra is nasty. Right? So, okay, what do we do if we can't solve for t? Now, I'm going to apply the following tool to the same example, even though we could solve for t in this case, but just to demo the second tool. Look for a relationship between the formula for x and the formula for y. And don't overthink it. Let's just think in kind of loose and flexible terms. They're both kind of first order polynomials of t. That they really actually do look a lot alike. They're not exactly the same, right? But it's not like one of them's full of arc cosecants and exponentials, and the other one is full of tangent and logs or something. That'd be weird, right? But here they're kind of not that different. So the idea is to try to figure out what do you have to do to the formula for x to make it look like the formula for y. Just think very literally about what is this process? What do I have to do to t minus 1 to get it to look like 3t plus 4? And well, of course, I'm going to multiply by 3. And then, let's see here, add 7. And as you do that to both sides of the equation here, notice the punchline is that you get a relationship between x and y. And in particular, you get the exact same relationship that we got by the previous method. Everybody with me? Another tool for your toolbox. Which one's better? I don't know. It depends. It depends on the circumstance. Right? If you can solve easily for t, then this one's nice. If you see a clear relationship between the two formulas, then this one's nice. So keep these tools in mind. Okay, here's a harder one. Three-dimensional. Right? You can tell it's three-dimensional because, let's see here, because the output has 3 coordinates. So this is a curve in space. Okay. Don't look for an equation. A single equation to describe a curve in space. Think about it, a curve in space, an equation in space would give you a surface, not a curve. So that's not going to work. What we can do in this case, and again, just another tool for your toolbox, break it down into parts. Right? We are interested in the whole parameterization, but if I look just at the x and the y part, forget about z for the moment. Let's just ignore z. And if you think about that, if you're ignoring z, then you're just looking at the projection down into the xy plane geometrically. And having done this, having decided we're going to ignore z, we look at cosine t, sine t. Hey, I recognize that. By the way, that's another really good tool for identifying parametric curves, is to remember when you saw them before, right? So this is a standard, very useful, comes up all the time, parameterization. Cosine t, sine t gives you a circle, unit circle in the xy plane. So this projection, not the parameterization itself, but the projection of our parameterization down into the xy plane is a circle. So whatever this curve is doing, I don't know, we haven't figured that out yet. But the shadow down in the xy plane going around in a circle. You can likewise say, okay, forget about x and y. Let's look just in the z direction only. Forget about x and y. I only want to talk about altitude. What's happening to altitude here? Well, another nice simple story. Altitude is just t. As the movie progresses, as we draw this curve, as time passes, t increases. Altitude increases exactly the same, right? So that tells us now 2 things. We have 2 bits of geometric information about our curve here. Our curve, aside from the fact that it starts at that point right there, our curve, it's going around in the projection, the shadow is going around in a circle. The height is rising constantly. This is a coordination challenge. Look at that. I can actually do it. Right? So this, okay, it's harder than it looks. Okay. Oh, man. This right here. Right? Try to put those pieces together. Not hard to persuade you, I hope. That makes a kind of a corkscrew sort of a pattern known as a helix. So we've gotten a pretty good sense for what this curve looks like by looking at components sort of separately. Everybody happy with that? Sometimes useful. Okay. where's my, oh, there it is. Okay. Here's a completely different category of questions about parameterizations. And you'll notice the three examples I've given you so far. The parameterization was given, and the question was, what does it look like geometrically? We're now going to do the opposite. We're going to say, hey, if I know what something looks like, if I have some information about a curve of some sort, how do I then create the parameterization? AKA, how do I parameterize? Parameterize means to create a parameterization. Okay, so we're going to undo, we're going to go backwards as it were. So here's my favorite method for parameterizing. I like to call it the graph parameterization. You'll see why in a moment. Neat fact, if you have a graph, we will talk a little bit more later about technically what a graph is, but it's this kind of a formula where in particular one of the variables is a function of the other. I hope y'all remember roughly that from, again, long ago, high school algebra. If you have a graph, the big trick, let t be whatever the input variable is. That's the trick. It's as simple as that. If you follow this trick, if you have a graph, let t be the input variable. Then the parameterization will fall into your lap. And here we go as an example. Suppose I want to parameterize this curve right here. Y'all remember this curve, right? We all know it's a parabola. How do I parameterize this parabola? Well, step one, I recognize that I have a graph. I have y equals. Y equals a function of the other variable being x. So, noted. Next, what does the trick tell me to do? Let t be the input variable. Okay, so x is going to be our input variable, and notice that's what I wrote right here. X is t. Said differently, my formula for position as a function of time has x. My input variable, its formula is just t. And then kind of game over, really, because if you think about it, if x is t, then this formula right here tells me what y has to be. Y has to be, well, it's x squared, so therefore it's got to be t squared. And sure enough, that is a parameterization then for our parabola. Everybody happy? Wonderful little trick. My favorite trick for parameterizing curves. Very useful in a lot of cases. Most curves, this is not technically true, but in practice, I think it's, this might be a slight overstatement. Many curves are graphs, and in those cases, this is great. Okay. Now, you'll notice sometimes a curve doesn't, at a glance, look like a graph, right? This does not present as a graph. This presents as, well, okay, some equation involving x's and y's. And then you think to yourself, can I solve for y? Because, I don't know, that's kind of what we're used to, right? Y is supposed to be a function of x. Isn't that how life works? Right? But you don't have to. There's no law. That alphabetical order is not really that mathematically significant, right? So, no, you can't solve for y, but you can solve for one of the variables in terms of the other. It's just that in this case, we solve for x. So, in fact, this curve, although it presents very differently, this curve is a graph. One of the variables, x, is a function of the other, y in this case. So again, the input variable in this case is y, so we let y be t. Right? If you have a graph, let let t equal the other variable, in this case y, and then again, that kind of automatically tells me what, in this case, x has to be. X has to be that right there. And again, parameterization. Right, done. Everybody good? All right. Okay, this next one is pretty wild. This is going to look like a much harder one. It's a little hard. Y'all have probably all seen bicycles riding around on campus at night, and they have a reflector, usually kind of near the tire part of the wheel, right? And as the bicycle goes, I've got it going to the right here, the wheel is both moving and turning, both. And altogether then, the reflector is going to follow this weird path. And again, I feel like we've all had this experience. You see the reflector and it kind of does this kind of weird ziggy kind of a pattern, right? Okay, how do we parameterize that weird ziggy pattern? And if you try to write it down with an equation, you're going to lose. It doesn't work very well. It's hard to, I'm not even sure if it's tractable to do that. If you try to make it a graph, y is a function of x, it's not good, right? Practically, it's certainly much, much less desirable than what I'm about to show you. So here's the trick. The tool for your toolbox is to recognize that where that reflector is, following this complicated path, right, is a sum of simpler things. A sum of simpler vectors. In particular, the axle of the wheel is doing something very simple. Right? The reflector's going all over the place, but the axle is just straight line. Yeah? And then plus, what I'm going to call this D vector. That's not very visible, is it? Let me write this in the pen. I'll do this in purple, sure. This D vector, and I emphasize now, I'm not talking about the arrow. I'm talking about the vector. And just as a reminder, vectors do not have locations. Right? Vectors have directions that they point. They have magnitudes saying how much they point in that direction. Direction and magnitude, no location. So you might think to yourself, oh, well, the arrow is doing something weird. But we're not interested in the arrow. We're interested in the vector. And the vector is doing something pretty simple. The vector is just going around in a circle. But I'm going to come back and look at those details. Okay, so that's the big idea. The big idea is to first recognize, again, if when this tool applies, when this is the right tool for the job, how the complicated thing that you're interested in is the sum of simpler things, in this case the axle and this D vector. Okay, now let's talk details. I need to understand A and D. Once I can write down formulas for A and D, then I just add them up. And let's talk about A first. Simple observation. Two simple observations actually. First of all, the height is that axle is always a distance A above the x-axis, right? It's the radius of the wheel, so that part's easy. Where it gets interesting is what can I say about here it is. What can I say about the x-coordinate here? How far has that axle moved? And now in particular, I need to decide what's going to be my parameter. Keep in mind, you always get to choose your parameter. I'm going to choose what I think is the most convenient thing here. There's different schools of thought, points of view. I like to have my parameter be this angle right there. Roughly speaking, because it's a lot easier to write distances in terms of angles than angles in terms of distances, right? if I need to solve for an angle, then I'm going to have arc sine, arc cosine, and I don't like it. That's weird and hard, right? But if I have an angle and I need to compute a distance, well, then it's just trig, it's just sine and cosine, and that's easier. Okay, so angles make good parameters in cases like this. I also like this particular angle because you'll notice that this particular angle defined like so, at this point here, this is where t is equal to 0, and as I go in this direction, t is increasing. So that's how I think of time as behaving, right? I like to think of time, when I start my stopwatch, it says 0, right? And then as time passes, t increases. So this angle is doing what time is supposed to do. Starts at 0 and then increases. Anybody buy it? Now that's a choice. Right? I didn't just prove anything. I just made a choice to make my life convenient. Okay. All right. So back to the axle. As I try to understand this axle. What can I say about that x-coordinate that we're trying to find? Well, that x-coordinate, another way to think of that x-coordinate is it is the amount of road that has touched rubber to that point. And physical appeal that I hope makes sense to y'all, the amount of road that has touched rubber is equal to the amount of rubber that has touched road. Now that's purely a physical appeal. If this is a dry street and there's no slipping, right? I mean, frankly, if the bicycle were slipping, it'd make the reflector take a very different pattern. So we're going to assume no slipping, right? And no slipping means rubber equals road. The nice thing about this is let's see here. Do I have? Yeah. The amount of rubber that has touched road is easy to write down. That's an arc of a circle. An arc of a circle is radius times angle, and so in this case, A times t. Everybody with me? Okay, so we are good then on A. A has that nice simple formula. All right, now let's talk about the D vector. And keeping in mind D is that vector right there. Well, of course, being a vector, I can draw it wherever I want, and naturally it's very convenient to draw it in standard position, tail at the origin, right? And keep in mind, now we've got to be careful with this, that T, again, is that angle. So I need to write this purple vector coordinates as a function of this angle T. And, well, that's just not the convenient way to do it, right? If I want to understand this purple vector, much easier to understand the purple vector in terms of this angle, theta. Right? That's the arbitrary but highly standard convention of how we think about sine and cosine as angles are measured from the positive part of the x-axis going counterclockwise. So I'd like to have D as a function of t, but what I can immediately write down, what's effortless to write down, is that D is a convenient function of theta. Now, having written that down, all I really need, if I want to turn this into, again, my goal is to have D as a function of t, I just need a relationship between theta and t. And if you look at this picture, I think it's a pretty believable pitch that, let's see here, I'll do this in yellow. Theta plus t is constant. As t gets bigger, theta gets smaller. They always add up to 3 pi over 2. So I can solve for theta effortlessly here now. Theta as a function of t, well, let me just leave it like this here. Theta, that thing here, as a function of t, is 3 pi over 2 minus t. And then this formula turns into this formula by way of the angle addition formulas. Side note, I am aware that a lot of y'all have been excused from knowing the angle addition formulas for sine and cosine for probably since high school trig class or whatever, whenever it was that you took that. And I guess in those contexts I won't judge, but just FYI, those formulas are extremely useful. They're going to come up in this class a lot. And they're going to come up in future engineering classes a lot. So I need y'all to know those formulas. And just to document specifically, I need you to know the formula for cosine of a plus b and the formula for sine of a plus b. You don't have to worry about like tan and secant and stuff like that. But these two, sine and cosine of a plus b, make sure you know those. That in particular is what allows you to rewrite like so. Yep.
Can you just repeat why the theta is equal to 3 pi?
Yeah, it's just a matter of looking at the what I have highlighted in yellow here, right? As this thing moves, as t increases, just notice that theta decreases, but these two angles, you know, however this yellow 3 pi over 2 is divided up, theta plus t always makes total 3 pi over 2. Yeah.
And so then minus t.
I'm sorry?
Oh yeah, minus t. Okay, yeah.
Yeah, no worries. Yeah. Cool. Is everybody happy? Yep.
For the vector A, what's the second coordinate? A not 0.
Oh, yeah, because you got to keep in mind what we're interested in. Wrong color. We're interested in the coordinates of the axle, and the axle is sitting up above the ground, right? You see what I'm saying? Yeah, and so so it's the height is a because a happens to be the radius, and the radius just happens to be the height of the axle. Yeah. Cool. Good. All right, so we're actually done now. It's just a matter of spiking the football. And we have made formulas, a certain amount of trouble, inconvenience for each particular part. But here's the A, and here's the D vector. And so grand total, our reflector is parameterized by this formula. And if you like, you can add these two vectors to get a single vector. It's how you write it down. I'm not particular. But A plus D. All right. Okay, so again, tool for your toolbox. There's various nice lessons in this example. One is that complicated curves, points on complicated curves, sometimes, more often than you might expect at a first thought, are actually the sum of simpler things, right? So look for opportunities to rewrite hard things as sums of simpler things. Comes up. And then various lessons. I think the rubber equals road is a nice little observation, foot in the door for one key part of this. And then thinking about angles and relationships. And there are a lot of detailed devils in here, right? But of course you have to be able to, write it down, label everything. Notice my picture is kind of decent. It's really helpful, right, to have a decent, clean picture. Everything labeled. Any relationship you're going to write down, label those things so that the picture kind of tells the story, right? Another nice lesson, I think, from this example. Okay, here's another one. Let's parameterize a line. And this is another one where I can break it down as a sum. So if I want to talk about this point here, a point on this line, again, if I imagine the process of drawing the line, right? Well, I can view that as being some fixed point x naught, which if you like, you can think of as being a vector, whatever, it doesn't matter. Some fixed point x naught plus then some multiple of a what I'm going to call a direction vector describing the direction that's parallel to the line. So point on the line plus scalar multiples of a vector parallel to the line, and this formula altogether gives me my location by that formula. So another example of something that, maybe, if you were to just, if you weren't to think of it, breaking it up into pieces like this, it could kind of feel like, well, this vector is doing the kind of, it's a straight line, but the direction is changing faster along in here and slower over there, and it's sort of asymptotically constant, and it's kind of, how would I describe, it's hard to get your hands on the vector x itself alone, but the blue point doesn't move. This is super easy, and this green vector is just literally scaling, just getting longer as time passes, right? So sum of simpler things, again, being the easy way to describe this more complicated thing. All right. Okay, moving along. Another tool for your toolbox. Sometimes the thing you want to parameterize is very similar to something you already know how to parameterize. So I like to describe this as deforming an existing parameterization. So here we go. Let's talk about this ellipse here. There's an equation of an ellipse. Y'all remember all your algebra 2 or whatever they call that these days. And this is an ellipse that has approximately this shape right here. In particular, this 3 in the denominator there makes this a 3 there, and this 2 in the denominator makes this a 2 right there. So again, flashbacks to high school algebra. Well, ellipses are deformations of circles. And here's the unit circle, and this is my existing parameterization. I know how to parameterize that unit circle. Old news. Okay, so how do I use my existing parameterization? How do I account for the deformation to give me a new parameterization? And it's a pretty straightforward observation here. Apparently, I need to stretch horizontally by a factor of 3. And okay, if you want to stretch horizontally, then all of your x coordinates need to be 3 times as big. So there we go. There I just stretched in the x direction by a factor of 3 by literally multiplying my x coordinates by 3. That make sense? Likewise, I'm going to apparently need to stretch in the vertical direction by a factor of 2. Okay, well, I need to multiply all of my y coordinates by 2. So notice what I've done. I've taken my existing parameterization, cosine, comma, sine. Right? I am deforming appropriate to what I understand geometrically about these two shapes. And the result is the parameterization of the ellipse. Everybody happy? And a quick little confirmation, if you want to just make sure that everything went as it should. You know what? I'll leave that there. You can take these formulas for x and y and plug in, and this equation works, roughly speaking, because this 3 gets divided out by that 3, and then this 2 gets killed by this 2, and what's left over is just cosine squared plus sine squared is 1, which works. Everybody's happy? All right. Cool. All right. it's very easy to conflate two structurally very different things. A parameterization, to be fair, does have an equal sign in how we write it down, and some people actually call a parameterization parametric equations, and it just grates on me a little bit because what a parameterization does is importantly different from what an equation does, and that's what I want to describe here. A parameterization is a point generator. It makes points. You put in a t, out comes a point on your curve. Okay, very importantly, that is not what an equation does. If you have an equation for a curve, an equation does not really naturally generate points. An equation tests points. You come to me with a point, plug it into the equation either works or it doesn't. Right? If the equation works, yes, that point's on the curve. If the equation doesn't work, nope, not on the curve. Does that make sense? So these are structurally very different. And it's, for one thing, I just believe, and you're going to hear me say this multiple times, that when things are different, we need to distinguish them with the language. And so it just irks me every time they use the word equation involved in a parameterization. There's no need for that. Parameterization is a perfectly good word. It doesn't have equation anywhere in it. That helps to distinguish between these two different things. How confusing is it to use the word equation to describe two very different things? Anyway, it bugs. So keep that in mind. These little lessons are what allows us to solve this problem. So here's a parametric curve. That's a weird parametric curve. It's not immediately clear what that is, right? But I've got some sort of a parametric curve, and I'd like to know in what points on that parametric curve are also on this plane. We haven't actually seen that this is a plane yet, but we will very soon. That this turns out to be the equation for a plane. So how would I find the point on the parametric curve that is also on the plane? How would I find the intersection? So the idea is this generates points. Okay, great. Generate some points. And then test to see which of those generated points works. We're literally going to test the generated points. So here's the generated points. We have formulas for what gets generated. What are the x, y, and z that gets generated? And then here, I test them. And so what I end up with, you notice, is a great big formula involving t, and of course I can just, group and solve, and I get two values of t. Those are the values of t that generate points that pass the test of being on the plane. Everybody with me? So the Legos just fit together sometimes, right? Parameterizations spit points out, equations take points in. And so, boom, fit them together. And victory. Now, one last little detail, of course. What we've gotten here are values of t. We weren't asked for what values of t does blah, blah, blah. We were asked for what the points are. So now that I know what the t is, I do have to actually take those values of t and plug them back into the parameterization to see what those actual points are. A little micro detail at the end. Does everybody see the big picture here? Cool. Okay, I'm hoping y'all might have seen this before in Math219 or Math221. How many people have seen symmetric equations for a line? Show hands. No, okay, all right. Oh well. Fine. So If you have a line in R3, recall we know how to parameterize a line in R3. So you need a point, and you need a vector parallel to the line, and then we write down this formula, right? This is a parameterization for a line in R3. This is a point generator for a line in R3. Cool, I want a point tester. How would I find a point tester? And recall, we don't really expect an equation to work. An equation of 3 variables, you would kind of expect to give a surface, not a curve, and a line is a curve. So, all right, well, here's the trick. Again, I wish I'd thought of this. I didn't. Somebody showed me. Somebody showed them. The big idea. One test, a way to test whether a point is on the line is just to ask directly, is there a value of t? Does there exist? Oh, here's that notation again. There exists some value of t, and then this notation here means such that. Right? So, is there a value of t for which the point that I'm interested in actually gets generated? That's not a very good test, right? What am I supposed to do? Just sit there and plug in values of t over and over and over and over again until I either get lucky and happen to generate the point I'm interested in, or I can't go through all the values of t, right? There's too many. I don't have that kind of time. I can't test all infinitely many values of t. So this is not a good test. But what we can do, keeping in mind that we're trying to figure out if there is a certain value of t, how about this? Solve for that t. And you can solve for that t in all 3 of the equations, right? Each of the coordinate equations. You can solve for this t in the x coordinate equation and the y and the z. Right? So now let's say it a little bit differently. I need to know, is there a value of t that's equal to all 3 of these things? And that's a much easier question. How do you decide if there's a value of t that equals to all 3 of these things? Well, if t has to equal to all 3 of these things, then all 3 of these things have to equal to each other. Is there a value of t that's equal to 6, 6, and 4? No. Right? Is there a value of t that is equal to 3, 3, and 3? Yeah, 3. Right? Silly. It's so obvious it's silly. Right? So this, you'll notice, though, is a point tester. Right? This down here, easy point tester. Whatever value x, y, z you want to test, well, compute these 3 things and see if they're all equal to each other. If they're all equal, cool, you've got a point on the line. If any one of them is different from any other of them, then no, they're not all equal. There is no such value of t, and that point is not on our line. Okay. Right. Okay, so I think we can finish this page. There's not much on this. Well, let's see. Is there? We'll see. Anyway, y'all have seen the dot product before, right? Fundamental construction in linear algebra. There's a bazillion things to say about the dot product, and y'all have seen them in linear algebra, so I'm mostly going to let y'all read about dot products. The one thing, a real quick observation, I think it's a good cultural reminder that the dot product is where inner products come from, right? Inner products are a big deal in linear algebra, useful in a lot of ways. But that's just a reminder. The main thing I want to point out is the verbiage, perpendicular and orthogonal. A lot of people mistakenly say that orthogonal means exactly the same thing as perpendicular. It's really close. Really close, but not quite. You got to distinguish between 2 things. There is this geometric idea of 2 directions making a right angle. That is a geometric concept. right? Right angle, everybody understands right angle. That's what perpendicular means. Then, now, closely related, yeah, but there's this algebraic idea of a dot product being 0. Purely algebraic concept, nothing in what's written down here is intrinsically geometric. This is just algebraic formula applied to algebraic objects gives this algebraic value. That's all algebra. So, importantly, we have then two concepts. We have two words. I like to pair them up. I think that makes sense, right? You have two distinct but closely related ideas. You have two words with which to describe them. So to me, the word perpendicular is intrinsically a geometric statement about a right angle. And the word orthogonal is intrinsically an algebraic statement about a dot product being 0 or whatever your inner product is, but in this class, only dot products. And just keep in mind, they're not exactly the same concepts. The 0 vector, in particular, orthogonal to everything. It's not perpendicular to anything because it doesn't point in a direction. It doesn't make an angle, right? Is this vector combined with the 0 vector, does that make a right angle? No, it doesn't make any angle, right? And so it either doesn't make any angle or it makes all the angles. Take your pick, but it does not make, unambiguously a right angle. So I strongly prefer to keep these two words distinct. Our book does not agree with me. Heads up for that. The book is a little kind of fast and loose with this, but I try to exert a great effort to keep these distinct. Y'all have a good day. See you later. Oh, and I'm going to send out an email later with a few sort of organizational announcements.
Oh, so we can go to right now?